Okay, here's an example which is very similar to the one on the quiz, 6a. And so it says a sub n is the number of solutions to c1 plus c2 plus c3 equals n. These are all integers, so I just didn't take out time to write that, but integer solutions. And with these requirements, the variable c1 has to be in between 1 and 3, including 1 or 3, so at least 1, but no more than 3. And c2 is just anything that's non-negative, so it can be greater than or equal to 0. c3 has to be between 0 and 2. So first thing up is the ordinary generating function, OGF, or just capital GF, and that would be f of x 2. So I need a factor for each of the three variables, and the factor is just going to be powers of x, and the powers of x are going to be what the variables are allowed to have. So x to the 1 plus x squared plus x cubed. That's for C1. Then for C2, it has a power of 0 possible. So that means I need to start out with x to the 0, or 1 plus x squared. And there's no upper bound, so that goes forever. You can show it with a dot, dot, dot. Of course, that's the one that's going to be replaced by its Maclaurin convergent function. Then finally for C3, that one will also be finite because it has the upper bound, so it'll be a 1 plus x squared. And that's it. I made this one fairly short to fit on the chalkboard. The one in the quiz is a little bit longer, but it's straightforward. You just have to put the powers that the variables can take those values. So real quick, the reason why ordinary generating function works here is that order doesn't matter to these solutions. The three variables are like three types of donuts, and finding a solution when you know what n is like buying those kinds of donuts in the amounts that add up to n. And the important fact is that the donuts go in a bag and they don't get arranged in a nice order like when you're making a pin number or a permutation. So that's it, except that it does need to be, and this will always be required, you can't just leave it with the dot, dot, dot. So you need to put it into a closed form. Remove dot, dot, dot. So this will be a closed form in x as opposed to n. So the answer would look like x plus x squared plus x cubed times 1 over 1 minus x. And then 1 plus x squared. And that is fine. You can leave it like that. There's always going to be possible further simplifications using algebra, but if you do some algebra on it, just be really careful. Don't mess it up. You could factor an x out of this. Sometimes you can factor the whole multinomial. We could write it as a single large fraction with 1 minus x in the denominator, but I'm just going to leave it. So then the next thing that you would do on the homework is to find some values of a sub n. We could do that here, even though I don't have the computer up to punch in larger ones. I can find a couple of small ones, like a sub 0. So a sub 0 should be the 0th derivative at 0 divided by 0 factorial. And the 0th derivative is just the original function. And 0 factorial is defined as 1. So that just was asking for f of 0. And I plug a 0 in for x into this answer here. Let's see if I can focus on it. And I get, oh, well, the first factor is 0. 0 plus 0 plus 0. And 0 times 1, and then times 1 equals 0. So that should make sense. We should be able to check that to make sure that it works. It says there's 0 solutions if n is equal to 0 up here. And yeah, that's true because of this 1. There's no solutions because C1 has to be at least 1. It can't be 0 itself, and none of the others could be negative, so there's no way to solve it if you make the right-hand side a 0. So I bet a sub 1 will also be pretty easy. So that's the first derivative, so you could just write f prime. Okay, so f prime of 0, since just dividing by 1. Even that, I don't think I want to take the derivative on the board. I'd plug it in to the computer and make it take the derivative since it's kind of long. But we should be able to figure out what the answer should be. The only way to get an answer if we put n equal to 1 is if C2 and C3 are both 0 and C1 is the 1. So there should be only one answer to that. Good idea to check it, but I think it's correct. And so on. For a much higher number, just do that derivative, plug in the 0, and divide by that factorial. But I should also do the inclusion-exclusion for this one. This is kind of review since we've done it before, but it was one of the trickier kinds of problems on the last test. So, for instance, let's go with n equals 5. Alright, so if n equals 5, just for review, what you would do is take the fifth derivative, plug in 0, divide by 5 factorial. So you can also find it with inclusion-exclusion, which gives you a double check on your quiz. You should get the same answer for both, but try really hard not to force that so that it turns into a really good double check. You know, if you get the same answer, it'll be independently. So this should come out to, I'll put the word check here. So let's see, inclusion-exclusion for this. So we start by taking care of this 1 that needs to be the smallest number C1 can be. That's like buying one of those kind of donuts. So the total would be n equals 5. Just write that here so I remember. And so the 5 minus 1 is how many that we still have to distribute among C1, C2, and C3, since I've already designated C1 to have that 1. Then there are 3 types, 3 variables. So plus 3 minus 1, choose 3 minus 1. And then I need to break some rules and subtract. So there are no rules on C2, but there's an upper bound on C1 and on C3. So I'll have 2 rules to possibly break there. So subtract, and first I'm going to break the rule on C1. If it's allowed to be 3, then 4 or bigger is bad. So this will be C1 greater than or equal to 4. Now if C1 is greater than or equal to 4, it's definitely greater than or equal to 1, so I've taken care of that already by setting it greater than or equal to 4. And that means that I have put 4 in C1 out of my total of 5. So I'll show the work. There's 1 left, 5 minus 4, to distribute among the other 3. I'm just going to put plus 2, choose 2 here. That's the 3 minus 1. That'll be the same every time. And then the other single rule is C3 greater than or equal to 3. So this will be C3 greater than or equal to 3. And at this point, though, I have to remember that C1 is still greater than or equal to 1. Because that's required. That has to always happen. So you can put that here too. C1 greater than or equal to 1. Because that's part of this one. C1 greater than or equal to 1. We're including only those cases to begin with. So I have to make sure I only subtract to those cases. And that means that there's 4 that have been designated again. 1 for C1 and 3 for C3. So again, it will be 5 minus 4 plus 2 choose 2. And there were only 2 rules, and so I need to add back in their intersection. And that would be both C1 greater than or equal to 4 and C3 greater than or equal to 3. So you can work that out. If C1 is greater than or equal to 4 and C3 is greater than or equal to 3, that means I would give 4 to C1, 3 to C3. That's 7 so far. 5 minus 7, that's negative. And so it's definitely going to be a small number choose a large number. It'll turn out to look like 0 choose 2. But even without plugging those in, I could see that there's no way to do that. So I'll put a plus 0. But if you worked out the 0 choose 2, you would say, 0 choose 2 has to be 0 as well. Can't choose 2 things out of 0 things. And so we could probably figure this out. This is 5 plus 3 minus 2. So I get 6 choose 2 there. 6 choose 2. So what I believe is 4 plus 3, 7, 6 choose 2. 6 choose 2 should be easy enough to figure out. 6 times 5 divided by 2. So you get 15. This one is going to be 5 minus 4 is 1 plus 2. 3 choose 2. That's 3. Same as 3 choose 1. And this one's the same thing. So I get the 15 minus 3 minus 3. So 15 minus 6 equals 9. Alright, hopefully I did that correctly in my head. I'll have to redo the video if not. But I think so. And now the double check would be to find fifth derivative, plug in 0, divide by 5 factorial.